Hi everyone, I'm Yanjun. Here I'm gonna talk about our framework PrivColl, which enables practical privacy-preserving machine learning. And this is a joint work with my excellent co-authors, Guangdong, Caitlin, Chen, and Ryan. The performance of machine learning largely relies on the availability of datasets. To take advantage of massive data owned by multiple entities, the collaborative machine learning has been proposed to enable two or more data owners to construct a joint model. And one typical scenario demanding the collaborative learning is where the features of the same sample are held by multiple data owners. And the collaboration among owners can improve the model accuracy by leveraging additional features from each other. Real-world applications can be mobile machine learning that utilize information from different apps of a user, or I recommend a system that takes use of ratings of the same item among multiple online merchants to enhance its predictive power. To address the privacy concerns arising from collaborative learning, many studies have been proposed to provide data locality by distributing learning algorithms onto data owners, such that the data can be confined with their owners. Despite this, the learning process still needs sharing locally trained models in order to synthesize the final models. However, these local models are subject to information leakage. For example, model evasion attacks are able to restore training data from the trained models. And to provide a supplementary, cryptographic mechanisms such as homomorphic encryption and secure multi-computation may be employed, but are known to be limited by significant overheads, especially on multiplication operations and nonlinear functions on ciphertext. To solve these problems, we propose PrivColl, which stands for Privacy Preserving Collaborative Study. This is a lightweight cryptographic framework for collaborative learning with distributed features. PrivColl guarantees privacy in such a way that corrupt parties are unlikely, that is, with a negligible probability, to review either the original data or the trained models from other honest parties. And it also achieves practicability by the redesigned workflow of collaborative learning. The main strategy is to dispense the homomorphic multiplication operations and nonlinear functions on ciphertext, and employs only the homomorphic addition operations provided by the additive secret sharing scheme for synthesized local models and intermediate outcomes. And by doing this, the framework retains high efficiency. For example, it achieves a speed up of 216 times faster over the state-of-art OT or LEHE-based schemes for training neural network. Not only to achieve the strong privacy and practicability guarantee, we also do not sacrifice the correctness of functionalities. And we demonstrate that PrivColl ensures the learned model is identical to that in the traditional non-distributed framework, and also supports any machine learning algorithms that use gradient descent for optimization. Here we introduce the necessary background knowledge in this work, including gradient descent optimization and additive secret sharing scheme. Gradient descent optimization is used to find the values of coefficient matrix W that minimize a cost function J, and it is derived by the optimization argmin of J. According to the Chen rule in calculus, the gradient with respect to W can be rewritten into this equation. As such, we can decompose the gradient descent optimization into delta, x, and tau, and distribute them to different computation nodes. And when these computation nodes collaborate together, these primitives can be recombined and to achieve correctness of learning. And we employ the homomorphic addition operations provided by additive secret sharing scheme. In the secret sharing scheme, each secret is split into shares which are uniformly distributed. This prevents any participant who has parts of shares from deriving the values of secret unless all participants join their shares. The scheme has a homomorphic property that allows efficient and secure addition on a set of secret values held by corresponding participants. To do this, each participant splits its secret into shares and distributes each share to the corresponding participant. Then, each participant locally adds the shares it holds and produces the sum of the shares. After that, a reconstruction algorithm which takes the sum of the shares from each participant and add them together can be executed by an aggregator to reconstruct the sum of the secret values without revealing any secret addends. Now we present the design of PrivColl. PrivColl adopts a two-layer architecture commonly used in collaborative learning frameworks, and this architecture has a local node layer consisting of participating data owners and an aggregate node. Each local node holds parts of features of the training samples and the corresponding local model trained on them. PrivColl aims to defend against an honest but curious adversary who follows the collaboration protocols and training procedures, but is intended to obtain the datasets or the local model parameters of other local nodes. The adversary may control the aggregation node and some of local nodes. And here we assume that at least two local nodes need to be out of the adversary's control, since if there is only one honest local node, then the comprised local nodes who has the sum of their shares, colluding with the aggregation node who has the sum of all shares, will be able to obtain the share of the remaining node by a simple subtraction. Keeping local data model private is one of the main properties PrivColl aims to achieve. We define such property as epsilon privacy, which means the probability of an adversary deriving the raw data or the local model parameter based on its knowledge is not greater than epsilon. Providing functional correctness is another property PrivColl aims to guarantee. It means that the output of function that takes as input a combined training dataset is the same as it takes as input its vertical partitions. Now we introduce the workflow of PrivColl. Each local node holds its own training dataset and randomly initializes its coefficient matrix. And in each iteration of gradient descent, each local node multiplies the training data matrix and the coefficient matrix and split the result into secret shares using additive secret sharing scheme and calculate the sum of all the shares it receives. And then the aggregation node collects the result from the local nodes and add them together to reconstruct the homomorphic addition result. And then the aggregation node is able to compute the delta and send it back to local nodes for updating its local coefficient matrix. And this redesigned workflow ensures that both raw data and local models are always kept within their owners. We now analyze the privacy preservation of PrivColl's learning process. We first investigate overall knowledge that can be learned by the adversary from the training iterations. We use simulation paradigm to prove that the adversary's knowledge in PrivColl is bounded within a certain range. In simulation paradigm, the security of a protocol is proved by comparing what an adversary can do in a real protocol execution to what it can do in an ideal scenario, which is secure by definition. In an ideal scenario, there is a trusted third party to whom the parties send their inputs. In the real model, parties run the actual protocol that assumes no trusted party. A protocol is secure if any adversary in the real model where no trusted party exists, can do no more harm than if it was involved in the ideal model. And more formally, a protocol securely computes a functionality if for every adversary A in the real model, there exists an adversary S in the ideal model, such that the view of the adversary from a real execution is indistinguishable from the view of the adversary from an ideal execution. And the adversary in the ideal execution is called simulator. And an distinguishability between the view of real and ideal guarantees that the adversary can learn nothing more than their own inputs and the additional information required by the simulator for the simulation. In other words, the information required for the simulator is the additional knowledge that adversary A can learn and can only learn from the execution. And we define the party knowledge as the overall knowledge that can be learned by the adversary parties. And it includes the party's own inputs and additional knowledge that can be inferred from the training iterations. By the simulation-based proof, we demonstrate this adversary's knowledge bound in PrivColl, which indicates the knowledge that the adversary can learn and only can learn other than their own inputs during the training iterations. And with this limited knowledge, we give our theorem of privacy preservation guarantee. We demonstrate that with sufficient rank of training dataset of honest party, for example, greater than 35, which is common in real-world datasets, PrivColl achieves 10 to negative 40 privacy. It means a negligible probability for the adversary to reveal either the raw data or the local model parameters of other participants. And now we analyze the correctness of PrivColl with distributing learning algorithms that are based on gradient descent optimization. This theorem demonstrates that if a non-distributed gradient descent optimization algorithm takes a combined training dataset as input, converges to a local or global minima eta, then executing PrivColl with the same hyper settings on its vertical partitions also converges to eta. And this is the proof sketch comparing this equation, which is a non-distributed execution, and this equation in which we decompose the computational primitives and reassemble the gradients. We can find that the coefficient matrix in both executions are updated using the same equation. Now we demonstrate efficiency of PrivColl. The performance of PrivColl are shown in the green lines in the figure. And we take the performance of traditional non-privacy preserving frameworks as baseline, as shown in the blue lines in the figure, and compare the performance with MZ17, which considered solution based on OT and LHE, which are illustrated by red lines and magenta lines respectively. And we conduct experiments on MNet's dataset and follow the same settings, including sample size and machine specifications with MZ17. And to be representative, we execute on both LAN and WAN network settings to simulate various network conditions in reality. The LAN setting captures the scenario where two or more institutions collaboratively execute computation on their own private inputs without revealing the input to each other or disclosing it to a third party. In such scenario, the involved parties usually communicate over fast, dedicated links. And in our experiment, the average network bandwidth is set as 1 GB per second. And the WAN setting, on the other hand, simulates a more realistic scenario where individual participants share their data over public network infrastructure. And the average network latency is 137.7 milliseconds, and the average network out throughput is 9.27 megabytes per second. As shown in the figure, due to the parallelization in the computing of the local nodes, PrivColl outperforms the non-private baselines in LAN network setting and achieve significant efficiency improvements over MZ17. And for example, PrivColl takes only 22.5 minutes for training neural networks, while it takes more than 81 hours with MZ17 OT-based protocol. At last, we use a recurrent neural network as a case study to illustrate the collaborative learning process in PrivColl. And this figure shows an example of a two-layer feed-forward RNN. Every neural layer is attached with time subscript C. And the weight matrix W maps the input factor X to the hidden layer H, and the weight matrix V propagates the hidden layer to the output layer Y, and the weight matrix U maps the previous hidden layer to the current one. And in PrivColl, each local node keeps its training dataset XL at every time C and maintains the coefficient matrix WL locally. And in the forward propagation, local node compute XL multiplied by WL, and XW is calculated using the additive secret sharing schemes in these two steps. And then the aggregation node compute output propagated from the input layer and the output propagated from the hidden layer. And in the backward propagation through time, the aggregation node compute the delta based on the output of forward propagation and send the delta to local nodes. Then the aggregation node computes the gradients of J with respect to U and V and update these two coefficient matrix. And then the local nodes compute the gradient of J with respect to WL and update WL respectively. To conclude this talk, we have presented PrivColl, a privacy-preserving collaborative learning framework for training machine learning models on distributed features with favorable practicability. And PrivColl guarantees privacy preservation for both the local trained data and the models trained on them, while ensuring the correctness of training processes. And in the future, we will extend our framework to support generic distributed datasets. That is, the dataset can be partitioned either vertically or horizontally or in a mixed manner. And also we'll focus on stale synchronous parallelism, which allows the local nodes to be off synchrony up to a certain bounded delay. Thank you.